Okay, so I think we're starting our live stream. Okay, let me just set things up here a little bit. Give me a moment. Okay, so welcome everyone. I don't see how many people have joined, but hopefully you can hear me loud and clear. We're on our second Jakarta Tech Talk, this time with James Roper, and he's going to talk to us about getting reactive with streams in Jakarta EE. So James, do you want to take it over, share your screen, and start presenting?
Yep.
Perfect. Just for everyone, please feel free to use chat. After James finishes, we'll have everything open for questions and answers, and I'm sure we'll be happy to answer your questions.
Okay. So thank you for joining. My name is James Roper. If you're on the East Coast, I understand it's the afternoon. If you're on the West Coast, it's the morning. If you're in Europe, it's probably late in the evening. And if you're where I am in Australia, then I'd recommend going outside and watching the sunrise while you hear this webinar. So I work for a company called Lightbend. We are the company behind the Scala programming language, behind Akka, Play Framework, and Lagom. And my role there is the open source software architect. Today we're going to be looking at some upcoming reactive specifications in Jakarta EE, focusing specifically on some specifications that are both finished and in progress in MicroProfile that we hope will be eventually adopted into Jakarta EE and can be used in popular Jakarta EE or Java EE application servers today. So the first thing we're going to look at is what is reactive? What do we mean when we say we're going to bring reactive to Jakarta EE? We're going to then look at what Reactive Streams is, which is a particular technology for doing reactive programming. And we're going to look at exactly how this is being used at some completed specs and some in-progress specs. So what is reactive? Now, when a lot of people, when reactive comes to mind, probably a lot of people will think event-driven I/O. So things like completion stage and completable future, things like, if you've heard of reactive streams, the asynchronous handling of events, asynchronous back pressure, perhaps the Java new I/O APIs and the asynchronous event-driven I/O capabilities there. And you would be right if you thought that that's reactive, because it is. But one problem that we see today is that people stop at that and they say event-driven I/O is all reactive is, and that's in no way true. Reactive is so much more. In fact, if you just stop at event-driven I/O, you actually don't get much value at all. You're able to perhaps use your hardware a little better, but the full potential of reactive offers so much more. So reactive is a set of architectural patterns for building systems that are responsive. So responsive means when you go to the system, regardless of what else is happening in the system, it should give you an answer. It should work within a reasonable time frame. And in order to achieve that, it needs to be resilient. So if there is a failure in a component in the system, it shouldn't bring the whole system down. It should be able to continue working even when failures occur. And secondly, it also, to be responsive, it needs to be scalable, both up and down, because we don't want to, it's no good to be able to just be having 100 machines running a system that only needs that one day a year. And so these properties of resilience and scalability underline what a reactive system should be. And due to these tenets of reactive, it's perfectly suited to solving the challenges of cloud-native systems. And in case you aren't aware, there is something called the Reactive Manifesto, which very neatly and succinctly summarizes what reactive is and why it's needed. So you can visit that at www.reactivemanifesto.org in your own time if you wish. So let's look at some of these challenges that we have in cloud native computing that Reactive seeks to solve. So cloud native opens many opportunities. What we can do when we go to the cloud compared to just running on our own servers is very broad, but it also introduces many challenges. So I'm not going to talk about all the challenges, but some examples are when you go to the cloud and you're running microservices, you don't have a single database. Okay, and because you don't have a single database, you don't have ACID transactions on your data on your global state. Now you might have each service that you're running might have its own database, and within that database you can have ACID transactions for updates. But because you have multiple databases, when you need to update multiple services, there's no way to do that in an atomic way. You don't have ACID transactions across all your services. And so consistency can no longer be taken for granted. Another challenge is that because you've got more services, you've got more network communication, you've got more deployment configuration, there's more moving parts, and so there's more that you can get wrong. And so consequently, cloud native systems are inherently more fragile. They're inherently more prone to failure. Now, people often talk about going to the cloud and because you've got so many machines there, you can build a more resilient application, but that doesn't happen automatically. If you don't carefully design and use patterns that allow you to take advantage of those machines to build a more resilient system, you won't end up with a more resilient system. You will end up with a far more fragile system than a typical traditional monolith. Cloud native does offer great opportunities to scale. On most common clouds, the resources, at least compared to what you usually need, are seemingly endless. But scaling also doesn't happen automatically. How do you do so horizontally? If you just apply your normal patterns that you had with a monolith, you'll find you run into bottlenecks very quickly. So I'm going to outline just a couple of principles in Reactive. Reactive is far bigger than this, but a couple of principles that Reactive, that architecting reactive systems that we use when we architect reactive systems that help to solve some of these challenges. Probably the biggest principle in Reactive is isolating services. And when we say isolate, we mean ensuring that these services can't have an impact on each other. So let's just look at a moment at HTTP communication. It's very common when building microservices in the cloud to use HTTP. gRPC is also becoming common. But these protocols are inherently synchronous. It doesn't matter if you're using asynchronous I/O. You're still doing a request on the remote system and a response, and if that system isn't running at the time, if it's not available, if it's not responsive, you won't be able to proceed with your operation. So HTTP depends on both services involved in the communication being responsive. And this offers an opportunity for fragility, because if one of those services goes down, then effectively both services down. You can't achieve the operation that you needed to if you're using HTTP to communicate between them. And this gets worse if you start involving more and more services, because each service that that has an HTTP call done to it, whether it's in sequence or transitively, is going to impact the overall availability of the system. So when you use HTTP for communication between services, you don't have isolation. Okay, HTTP is not a reactive architectural principle. So you might think, well, we'll use a message broker to communicate between services, and that's a good idea. And so you might, as part of your operation, you might update some state in your local database and then publish a message to a message broker. There's still a dependency here, because it means the service that is trying to complete the operation must be responsive at the same time as the message broker. And if, for example, that service does an operation and then tries to publish a message to the message broker and the message broker isn't responsive, then that operation is going to only partially complete. Whichever order you happen to do it in, maybe you decide, well, okay, I'll publish to the message broker first and then commit my transaction. And let's say that the publish to the message broker succeeds, but then your database transaction fails, then you still have a partially complete operation. And so it's better, because usually it's easier to keep a piece of infrastructure like a message broker available, but you still don't have complete isolation there. So what we really wanted to try and do is make all operations asynchronous. And this is done using CQRS. So if you can separate your commands, so the things that come in and update your local state, from queries, and that includes publishing messages to a message broker, then you end up having no dependency between the responsiveness of any component, and you achieve full failure and scaling isolation, and are able to take the full advantage of your cloud-native platform. The second principle that I want to talk about is adopting programming models that manage failure. So in a traditional system, in a monolith, perhaps running Java EE or not, ACID transactions are there to handle failure for you. A developer doesn't need to explicitly handle all the failure conditions. They don't need to anticipate all the possibilities. What happens if something else tries to update this at the same time? What happens if either my service or the database goes down halfway through? They don't need to worry about, what do I need to clean up if there is a failure? What compensating actions do I need to do? Do I need to retry? ACID transactions handle that for you. But as we said before, in cloud-native systems, we don't have ACID transactions at a system level. And so the moment that we need to do an update that involves multiple services, we no longer have anything that manages failure for us. But we do want something that manages failure for us, because we don't want to have to manually implement handling for all the permutations of failure conditions that could happen. And so we need a different pattern for managing failure, one that isn't manual, one that we can take for granted, that we can focus on solving our business problems. Sorry, I think I had a problem with my headset there. So streams are the cloud native equivalent of ACID transactions. In a streams are an architectural pattern that we can use to be able to not worry about failure anymore. So let's take a look at this. Reactive streams, you may have heard of, is an approach to streaming that is reactive both from a programming perspective and from a systems architectural perspective. At a high level, reactive streams offer a declarative way of describing work to be done. And this is a declarative way of describing work is important because what you don't want to be doing is saying, okay, I'm going to, for example, read some message, and then I'm going to process it, and then I'm going to send a message here. Because if you're the one that's controlling what's done when, then you also have to manage the failure. Rather, what you just want to do is declare, well, here is my processing for these messages, and I want to let the infrastructure go and handle lifecycle and failure and retries for me. And distribution as well, because when we go to the cloud, we potentially have many machines, and we don't want to have to manually spread that load across our machines ourselves. Reactive Streams offers asynchronous handling of events, so it ensures that we have efficiency of resource use. If we can run many streams at once without consuming many threads. And Reactive Streams also propagates back pressure. And back pressure propagation is very important because without propagating back pressure, there's no way for a downstream processor or consumer of data to be able to push back to upstream processors and say, hey, I'm not ready to receive more data yet, can you please slow down? There are some APIs in Jakarta EE at the moment that offer asynchronous handling of events without back pressure. So the WebSocket API, for example, there's no way to go back to a WebSocket and say, hey, can you actually push back on the TCP connection to stop the client from sending me data? You have to handle it all, and if you can't, well, either you're going to run out of memory, or you're going to somehow, or you just have to fail. So at an implementation level, Reactive Streams is a specification effort that was started by Lightbend, Netflix, and Pivotal and others in 2013. That's 2013 when the initial contact and discussions were made, and then it was worked on through 2014 and finally released in 2015. It was adopted in Java and JDK 9, and so you can find this today in the Java Util Concurrent Flow API. It's considered a low-level integration API. So the interfaces in Java Util Concurrent Flow, there are 4 interfaces: publisher, subscriber, subscription, and there's also processor, which is just implements both publisher and subscriber. And there's only, I think, 7 methods across these interfaces. But these interfaces are intended for use for integrating between different asynchronous streaming libraries. So if I have a database that is able to asynchronously stream me rows, and I have a HTTP client that is able to asynchronously stream out bytes. And then I have a stream manipulation library that's able to do asynchronous transformations that convert these rows to bytes. I can connect all these things together using reactive streams, even if the authors of these technologies had never heard of or tested each other against each other. And that's what reactive streams offers. It does require high-level user-facing APIs. And an important point to make is that users should never implement reactive stream interfaces directly themselves. If you're using reactive streams and you find yourself implementing a publisher or subscriber, then you're probably doing things wrong, because even though it's only a few interfaces and about 7 methods, the spec for reactive streams itself has 40 or 50 individual requirements. There's a TCK that can be run against an implementation, which includes around 100 tests, and getting them to pass is a lot of effort. It's a lot of concurrent programming, dealing with memory barriers. It's not intended for users to implement directly themselves, rather they need a high-level user-facing API. Unfortunately, there are plenty out there. So you have your connectors to databases, to message brokers, to HTTP clients that implement reactive streams, and you also have streams manipulation libraries such as Kafka Streams, RxJava, and Reactor. So when you do work with reactive streams, you can bring in these libraries and do whatever transformations you need on the streams. Of course, when it comes to Jakarta EE, a challenge here is that these are all vendor libraries, proprietary libraries. They may be open source, but they're not standards. They're not something that can just be included in a Jakarta EE implementation. And so to address this in MicroProfile, I'm going to introduce our first specification, and that's the MicroProfile Reactive Streams operators. So this specification is a high-level user-facing API for manipulating reactive streams. We've just released 1.0, so you can use it. There are a number of implementations out there that you can try. It draws inspiration from Java util streams. So if you're familiar with Java util streams, then a lot of the methods are the same. The scope of what methods are included and what aren't are the same. I should point out that even though the APIs look similar, the underlying of what you're actually doing is very different. So Java util streams is about manipulating collections of things that are usually in memory, or they're calculated somehow on the fly, potentially in parallel. It's about bulk processing operations that don't involve I/O. Reactive streams, on the other hand, is fundamentally about handling I/O, about being able to process things asynchronously, about being able to push back up the stream with back pressure. Reactive streams, the implementation combines the best of Kafka Streams, RxJava, and Reactor. So every feature that we added, we looked at all those 3 of these popular implementations, and we looked at, okay, what naming convention do they use? What are their edge cases? How do they handle different things? And tried to come up with whatever was common and whatever seemed to fit best based on the experiences of those libraries. And we have 3 implementations so far. So there's one that's Kafka Streams based, one that's RxJava based, and we've got another one that doesn't have any dependencies, so it's been implemented from scratch. And the intention for that one is, if this was to ever to be adopted into the JDK itself, that might become the reference implementation. So what I will do now is take a look at some of the API docs for these. So here is processor builder. This is for a processor builder is for building generic transformations. So the kind of methods that you have are things like map. You can see we have these diagrams for what it actually looks like. So you have an incoming stream that has elements 1, 5, and 3. And if the map transformation is to multiply it by 10, you get out 10, 50, and 30. An example of flat map, we can see down here other ones. Filter, so filter everything that's less than 3. And so these are the kinds of operations that we have. Skip 3 elements, so the first 3 are skipped, and then you get 2 and 4 out. Now, I could give a demo of these, but chances are, if you are familiar with Java 8 and went to any conferences around the time that Java 8 was released, you've probably seen plenty of demos of Java util streams. That's not much different from just using MicroProfile Reactive Streams operators in isolation. The code looks very similar. It's the same sort of methods. And using Reactive Streams operators out of the context of actually doing asynchronous I/O processing really isn't interesting. You're much better off using Java util streams. So before I give a demo of this API, I'd like to move on to the next spec, which is something that actually uses and provides a use case for these operators to do some I/O processing. And that's MicroProfile Reactive Messaging. So it's a Reactive Streams-based messaging API. Messaging is in communicating through a message broker or through doing messaging peer-to-peer. It essentially provides 2 annotations, incoming and outgoing. You put these on methods in a CDI bean, and that declares this method provides something that's going to handle incoming or outgoing messages. It can be connected to any messaging provider, so we have implementations for Kafka, AMQP, MQTT, JMS. It's been designed so that it's not tied to any one messaging provider. The spec is currently in development, and we're targeting MicroProfile 3.0 for it. And so I'll now move on to a demo. So I've got an application here. So this is an online auction. It's somewhat like eBay. So I'm just going to create an item here. I want to auction off my bike.
Hey, James, if at any point you can check the chat as well with some questions, that would be great. Or maybe afterwards, after the demo.
Sure. I'll do it afterwards.
Okay, perfect. Thanks.
So I've created an auction. I'm selling my red bike, and I'll start the auction. And now with this very secure authentication, I'm going to log in as a different user. I'll place a bid. Place a $10 bid. You can see currently that's been accepted with a price of 50 cents. And then if I go and log in as someone else, now let's say this John user goes and they're really interested in red items. So they search and my bike comes up. Now you see here the current price is not listed. And the reason is because I have failed to implement something in this service. So we have a number of services implementing this application. There is an auction service or an item service that holds the details of the item. There's a bidding service that controls bids, and there's a search service that implements this search screen. And the way the search service gets its information is by subscribing to Kafka topics that from both the item service to get the information of the items, as well as the bidding service to get the current price. So if we go and have a look at the code, this is where it's subscribing to the bidding service. So you can see here we've got this incoming annotation, and it's saying I want the bidding bid event topic. This is returning a subscriber builder. So this is the MicroProfile Reactive Streams operators API here. It's going to build a subscriber of bid events. And then we create the builder here, and you can see we're doing nothing with each message. So obviously we haven't implemented it yet. We have implemented here up here the item event processing. So that's why the item appears in the search index at all. But the price isn't appearing because we haven't yet implemented handling of the bid events which contain the price in them. So why don't we do that? So the first thing that we want to do when we receive a bid event, this service actually persists its data inside Elasticsearch, and Elasticsearch works with documents. So we want to first convert our messages using the map function into documents. So I've already created a method to do that, bid event to document. Now this method actually doesn't want to handle all events. There are some events that don't need to persist anything as a result, and so it actually returns a type of optional. If the event is not one that it's interesting, it will return an empty optional. So the next thing we want to do is filter out all those empty options. So we'll use filter to do that, and we'll use optional is present. So if that method returned a document, then it'll still be in the stream. Otherwise, after this filter operation, there won't be any element in that stream for that. Now, next thing, so our message is still wrapped inside an optional. So let's unwrap it using optional.get. So now we have our documents that are flowing through our stream, not as optionals, just as direct elements. And so now we can actually handle them. We will use flat map completion stage. So we have a reactive or an asynchronous Elasticsearch store here. So we'll do index store.store, and we'll pass in the document. Need to pass in the message there, message.getPayload. Now the result of that store operation is a completion stage of done, which is just a unit operation. We're going to map that to convert it back to the message, because after storing it, we want to then acknowledge the message from the Kafka queue. So we now we've stored it, but we've still got our stream of messages, so we can do flat map completion stage, and we can invoke the ACK, which once again is an asynchronous. Which is why we use flat map completion stage. And after that, we've actually done everything that we need to do. So we just terminate the stream with this null up on each element, and then we can return that as a subscriber of message events. So having implemented that, I've got this application running in the background. Lagom automatically detects changes to code, recompiles, and restarts services. I should mention that this application is written in Lagom, which is a reactive microservices framework. So that should have reloaded, and if we do the search again, we don't see the current price. And the reason is because there's something else that we haven't implemented yet. But before I get to showing that, I'll move on to the next slide. So another thing that's come up in discussions of recent in MicroProfile is the possibility of a CQRS spec. Now, CQRS stands for Command Query Responsibility Segregation, and it's about separating the responsibility of handling commands from the responsibility of handling queries, such that they can be handled in different databases, they can be scaled independently, and more importantly, what we're interested in here is we don't want them to be able to impact each other. So if a query fails to, if the query handling fails for some reason, that shouldn't stop our commands from being processed. And you would have, earlier in the presentation, I talked about how we can handle, about how if you publish directly to a message broker after you do an operation such as an update in the database, then you have a level of coupling with your message broker here. CQRS can be used to decouple that your persisting of your handling of your command from then publishing those events to the message broker so they can update queries. So let's take a look back in our service. And we're going to move now into a different service, into the bidding service. And this is the code that I've implemented that publishes the event log. Now, I'm not going to show the actual persistence for the bidding service, but what the bidding service does is when it's using event sourcing, and so rather than storing the current state of an auction, such as this is the current price and this is the current winning bidder, and the auction is still running, rather than storing that state, it simply stores all the events that happened and computes the state from the events. So auction started, this bid was placed, this bid was placed, the auction's finished. And because when it does that, it stores those events in an event log. That event log can be consumed asynchronously by another process, in this case, this publish event log method. And so we have this decoupling from the persistence where these events were persisted, and the thing that then goes and in another process, potentially on another machine at a different time, goes and reads that event log and publishes it out to Kafka. So you can see once again, this time it's not a subscriber, it's a processor, which means it transforms messages. We create a builder and we filter them to only publish the ones that we want to filter, and then we do some transformations on them. And we end up converting these incoming messages of the auction event, that's what gets persisted to the database, to these bid event, which is what we end up publishing to Kafka. And what we're missing here is annotations to be able to declare this. So these are the reactive messaging annotations, and here I'm saying the provider is the event log. So this isn't actually getting messages from a message broker here. It's getting messages from our database, from our CQRS event stream, and they're going to be used as incoming messages, and then outgoing we will publish to that bid event queue in Kafka. And so now I've made these changes, and when Lagom picks that up, recompiles, restarts my service, I can go, I can hit search, and hopefully it should show the current price. I'm not sure why it's not doing that. We'll try posting another bid just for good measure. Okay, so the price now there is published. Now, unfortunately, I've given this demo a number of times before, and what happens there is the current price just comes up. I'll have to go back and work out exactly why it didn't come up then. Possibly there was something wasn't connected to Kafka. Sometimes in development, I find Kafka can be a bit finicky. But an important thing that if the demo worked, it would have demonstrated is that we actually had a self-healing system there. When I at some stage as you saw, I hadn't even implemented the publish. Now, if we had published directly to Kafka after doing our operation, then we would have had, our system wouldn't have ever got those current price, those bid events, because they were lost in history. You can't republish, you can't redo something from the past. But when you work with streams, when you take a stream-oriented approach to the system, then you can resume that processing at any time. And so you get these self-healing probabilities where the stream itself is what continues pushing your system to be consistent. And so that's the end of the presentation. There are some links here that I've got. You can see the MicroProfile Reactive Streams operators spec. Here's the documentation for the operators, which I showed before, and the MicroProfile Reactive Messaging spec. So I might check if there are questions now. I can't actually see any questions in the chat.
Oh, you don't?
Yeah, do you want to read them out to me?
Oh. So let me see. I'm trying to figure out if I can point to you the questions, but nevertheless. So one of the questions that we have is, what is CQRS? And then, you know, the link was provided for that, but if you wanted to go over that, did you have any comments?
So yeah, I did mention CQRS early in the presentation without explaining, and then I did explain a bit more detail later, but just to go over it again, it's command query responsibility segregation, and the idea is to separate your commands, which are your write operations, from your queries, which are your read operations. And so what you end up with is you do some command, you handle your write operations, and then you have a stream of events that are the output of your write operations, whether it's event sourcing, where the events themselves are what you persist, or in addition to doing some updates on a CRUD database, you might persist some events to an event table. You can then consume those events. Usually they will have some sort of offset, and so you can track where you are into the offset, which means when you fail or when something goes wrong, you can resume from that offset. And it allows you to be able to do that processing on different machines. You can use different database technologies. So an example here, I'm using Elasticsearch for the search service, which is a different technology to Cassandra, which is what's been used in the item service and bid service. And because it's streams based, you can take advantage of the fact that you can let the infrastructure manage your streams for you to manage your failure, retries, distribution.
Right. Another question is do you support, or is this working with Vertex?
Yeah, so Vertex, one of the implementations of Reactive Streams operators is it has been implemented by Red Hat on RxJava with also support in Vertex. And indeed, the Red Hat's messaging implementation is built on Vertex. So the work that I'm doing is with Kafka Streams, and Lagom. But if you go to Red Hat's MicroProfile implementation, you'll get support on Vertex.
Great. Another question is, what is the benefit of using this over the plain Kafka Streams API?
Okay, so Kafka Streams is Kafka to Kafka. You can do Kafka Connect, but it's very limited. Kafka Streams, they say they support event sourcing, but they only support something that looks vaguely like event sourcing. It doesn't support commands. It's just events that must be handled and can't be rejected, which is a fundamental thing of event sourcing, is that you can validate and reject commands. So if you need to do Kafka to Kafka processing, then Kafka Streams is great. But what this gives you is so much more. You can, as you saw, you can connect an event log in a database to your to a Kafka queue. It's also there's no Kafka specific code, or there doesn't have to be any Kafka specific code in your application. So you can do your Kafka to Kafka event processing without being tied to Kafka, and be able to move to different message brokers. For example, the cloud technologies like Kinesis or Azure Event Hubs are very Kafka-like. Your code will be portable to those. So this allows you to do things without the vendor locking that you get with Kafka Streams.
Okay, let me see. I need to thank Eclipse MicroProfile community for kind of answering questions, and also they're quite active in the chat as well. So let me see. I think you already said that the example you provided is on the GitHub. Is that right?
Yep, the example app itself. I think I have a version of it which is a bit different from another presentation, but I can publish it to GitHub.
Yeah.
I'll publish it to. This is where I'll publish it to. That doesn't exist yet, but Jakarta EE Reactive Streaming. That's where you'll be able to find it probably 5 minutes after this presentation is finished.
That's fantastic. Maybe if you don't mind, put it on your last slide, yep. So people can view it from that perspective as well, and have the link there. Okay. Any more questions, comments for James? We want to keep James around to answer more questions. So please, if there are any questions or comments whatsoever on the talks, please put it in the chat. We're super excited to see you, that you dialed in, and then that there is activity on the chat. Okay, so if there isn't anything else, a reminder that in a month we will have another call. I'm just about to set it up. I'm hoping to either have Emily Jian or Sebastian Daschner to have their tech talks. So stay tuned and kind of monitor for the date and time. And in the meanwhile, I want to thank James very, very much. It is greatly appreciated. And yeah, we'll stay in touch, and we know where to find James if we need him to, provide more information with regards to streaming or reactive streaming or anything else. Bye for now, and staying warm, particularly us on the northern hemisphere, where it's still freezing. Okay. Thank you, everyone, and we'll be in touch.
Thank you.